or in Canada in 1984 and 1986, respectively. From 1979 to 1980, he was with the Research and Development Center of Kyotron, Trivandrum, India. From 1987 to 1992, he was with the Research and Applied Technology Division of Black & Decker Corporation, Tucson, MD, USA. From 1992 to 2013, he was with Delphi Saginaw Steering Systems and Next Year Automotive, Saginaw, MI, USA, where he was the Chief Scientist at the Innovation Center. He is currently the Director of Motor Drive Systems at Halla Mechatronics, Bay City, MI, USA. He has authored over 50 technical publications and holds 31 US patents. His current research interests include electrical machines and variable speed drives. Dr. Sebastian was a co-recipient of an IEEE Industry Application Society Transactions First Prize Paper Award. He was the recipient of the 2010 IEEE Industry Application Society Outstanding Achievement Award. He has held several positions in the Industrial Drives Committee and in the Industrial Power Conversion Systems Department, and currently the president of the IEEE Industry Application Society. He was the general chair for the first IEEE Energy Conversion Congress and Exposition held in San Jose, CA, USA in 2009, and the co-general chair of the IEEE Power Electronics, Drives and Energy Systems in Bangalore, India. He is a fellow of IEEE and immediate past president of IEEE IAS Society. Say, we welcome you to the platform.
Oh, I'm sorry, I was on mute. Sorry. Can you hear me?
Yes, sir, you're audible.
Okay, you can see the slides?
Yes, sir.
All right, good. I am ready to go then. Thank you so much for inviting me for this presentation. There was a correction. Actually, I am not the current president of Industry Application Society. I'm just the past president of the Industry Application Society. So I would like to, what I want today is I want to go, first of all, I want to apologize to some of the people. I don't know whether, during the last few months, I have made few presentations to various groups in India, and I think I'm running out of new contents to present. So if you have already attended one of them, maybe this will be a duplication somewhat. So I apologize for that one. So with that, let me go into my talk. So I will be talking about some of the activities which are happening in the automotive industry in terms of the developments, especially in terms of the electrification aspects in the vehicles. When I say electrification, you may be thinking of electric vehicles, but I'm talking more in terms of all the other things, including the electric vehicle stuff. But there are a lot of other things which are happening in the vehicle to make the vehicle more electrified. So that is what I'm trying to cover here. Okay, so if you look at the history, the first mass-produced car was by Ford Model T, which was introduced in 1908. At that time, really, the electrification was a 6-volt battery and a dynamo and a couple of lights, and that was the extent of electrification at that time. Up to about 1940s, the battery voltage was still 6 volt, and around that time, around 1940, 1950 time frame, the car battery changed from 6 to 12 volt, and I think even today, when you buy a car, most probably you have a 12 volt battery in that car. So that's where we started from. But if we they sold almost 15 million cars in the about 20-year time frame, this car at that time. Now, from that Model T, if you look at today's car, there are a lot of things which are electric in the car. I mean, starting from all these navigation stuffs and human machine interfaces, electric power steering, which I'll cover a little bit, the anti-lock brake systems and tire pressure monitoring system. If you go down, places like where I am from, where it's very cold, we need heated seat, heated steering wheel. We have electric water pump and electric AC, and with the advent of all the hybrid and electric vehicles, we have the chargers and the motors and inverters and DC-DC converters, you name it. It's a lot of electric stuff in the car today. So the electrification and the advanced control in the vehicle are accelerating at a much, much faster rate, and that is I'm covering today. So if you look at the electrification, why do we want electrification? It is mainly because of 3 or 4 reasons. I would say safety, fuel economy and emissions, driver comfort and convenience. And I think these are mainly the factors which are driving why do we want to go for electrification. So let's talk a little bit about the safety aspects. So if you look at the car today, you have a lot of things in the car which are there to protect the driver in case of an accident. For example, you have the seat belt, you have the airbag, all that stuff is there to protect the driver if there is an accident. That doesn't do anything to minimize or to avoid the accident. They are there to protect the driver in case of an accident. Now, from there, the next generation is really passive avoidance systems, which are there to warn the driver, but the driver still have to take the action to avoid the accident. For example, you can think of lane departure warning. If you are going on a multiple line highway and if you are drifting from line to line, that means you are probably sleepy or drowsy or whatever it is, and the car can warn the driver by alerting and giving an alarm or vibrating your steering wheel or seat or something. No, this is just giving advance warning to the driver, but the driver has to take action still. So these are really passive mechanisms: the line departure warning, the side detection, the automated front. If your car goes very close to the car in front of you, it can give you warning and things like that. And the car can even monitor the driver's eye and see whether the driver is sleepy. These are all things to warn the driver to avoid the accidents. Now, the next generation of these systems are what is called the active safety systems. In the active safety systems, the car now will start doing things to make the car more safe or avoid accidents. For example, I think from 2022 onwards, many countries are mandating that the cars should have adaptive braking systems, in the sense that if the car in front of you slows down, even if the driver is not applying brake, your car has to slow down. So now the car is actively taking part in making the vehicle more safe. So that is one aspects. Now, there are several. You can also imagine that, if the car is going to roll over, you have enough sensors and things like that in the car to analyze and find out that the car is going to roll over. We can use the braking or the steering to avoid that. Now the car can do that because today the car has our control systems and digital signal processors and everything which we are using can do all these computations at a very fast rate and command the steering or braking at the appropriate time and get the car to a safe state in very fast time. this means that all these computations and sensing and computation has to happen in milliseconds, not in seconds. So now we are able to do all these things today, and these type of systems are helping to minimize the accidents. So you have probably seen many of these type of sceneries on the side. I think all these systems are trying to put an end to these sceneries, or at least minimize these sceneries, and for the car to actively take part in making the vehicle and the passengers safe. So that is the objective of a lot of this work, and the electrification is allowing us to do all these things. Now, if you talk about fuel economy and emissions, I will talk about one of the areas where I spend a lot of time working on, which is the steering systems. When I joined the automotive industry, at that time, all the cars which we buy used to have what is called hydraulically assisted steering system. So in the hydraulically assisted steering system, there is a pump which is connected to the engine, which produces high pressure fluid, and the high pressure fluid is ported into a piston cylinder arrangement. And when the driver turns his hand wheel, a valve mechanism opens and ports this high pressure fluid into appropriate chamber to help the driver. And that's basically the basic mechanism of the hydraulically assisted system. Today, if you buy a car, most probably you will be buying a car with electric power steering. All the hydraulics and pumps and hydraulic fluid and everything is replaced, and it is being controlled by an electrically assisted motor, a motor controller and a sensor and a gear mechanism applies the torque to and helps the driver to steer to steer the car. So this is the basic fundamental thing of the electric power steering. Now, this was a huge transformation for the automotive industry over the last couple of decades. Basically, we transformed the whole industry from an hydraulically assisted system to electrically assisted power steering system. This actually saves a significant amount of fuel economy, because if you look at the hydraulic system, the pump is working all the time as soon as you turn the engine on. When you are going on a highway, when you really don't need much of a steering, your pump is working at maximum speed and we are producing a lot of loss. Whereas in an electric power steering, that motor runs only when the driver turns the steering wheel. So other than that, the motor doesn't produce any power or torque or anything. So speaking, it's an on-demand system. So there is a significant fuel economy with the electric power steering. So if you look at the electric power steering car, depending on the size of the car, there is a fuel economy advantage of 0.2 to 2 miles per gallon advantage. And if you look at the number of barrels of oil we saved because the electric power steering, it is tremendous over the last several years. So the other example of fuel economy is really the electric car. In this case, you can see that the battery is placed at the bottom here, and we have a motor controller and charging systems and everything in the car. And this is ultimately the ultimate saving of fuel economy in terms of the emission and all that stuff. So I'll talk about a little more on this one later on. Now, one of the challenges for the engineers is, this picture is the front compartment of a Tesla car, basically. Okay, you can see that the place where we used to have that huge engine and everything is now being used to carry the luggage and the personal belongings of the driver and passenger. So it is the engineer's responsibility to see, how we can package all your motor and everything into a smaller space so that the space can be used for useful to the passenger and driver. This is one of the challenges which we have. if you talk about the electric vehicle, and if you're talking about the space, how can I utilize the space effectively? One of the area is the tire. Inside the tire, there is some free space. Can you package all our motor and controller and everything inside that? Then you don't need the engine compartment really, because that's all gone. So this is an example in which the motor and the control, and in addition to the drive motor, the control, in addition to that, the steering, suspension, and braking, and everything is integrated into this module, what we call it's a corner module. Of course, this is not in the market yet. This is all in the development stage now. This is going to take some more time. There are a lot of challenges to make this productionized. You can imagine the environmental conditions, in this motor and controller has to go through to survive inside the tire, and dissipation of heat, and all these things there are a lot of challenges to make this really viable commercially. So, but people are working on it. So you might see that in several years, probably a couple of years at least. Now, the other one is the driver comfort and the convenience. If you think about the ultimate driver comfort and convenience, you probably will. We'll be talking about the autonomous vehicle where driver really doesn't have to do anything. Car will drive by itself and will take from point A to point B, and that's the ultimate convenience, basically. Now, when we talk about the advanced safety architecture and autonomous cars, now our design thinking has to change in terms of how to make the vehicle more safer. So in a conventional car, certain failure modes are acceptable. That is acceptable in the autonomous vehicle. So from a design point of view, what we use is what is called automotive safety integrity levels. Depending on how safety critical is the function of that electrical module, we categorize that into several modules like QM, A, B, C, and D. When you say it's an ASIL D level, that means it is a very highly safety critical system. If that system fails, that will create an accident or endanger the driver. So we have to make the safety critical systems ASIL D so that system can never fail. For example, the steering system is really a safety critical system, especially if you think about an autonomous car. If the steering system fails, the car is completely going to be in trouble. So you cannot afford to fail that system under any circumstances. So that is why that's what we call ASIL D type of system, where you have to have systems to monitor and make sure that it doesn't fail. So if this is again, I'm showing few of the electric power steering mechanizations. Let's take the middle one. Okay, in this case, the motor and controller is assisting the driver right at the what is called the rack of the system. Now, in a conventional steering, the car you're buying today, if something goes wrong and something fails in the motor or the controller, we shut the system off, and the driver can steer this car with, of course, heavier effort. So but at least the driver can bring the car to a safe stop on the roadside without too much of a problem. So shutting off the system is considered an acceptable failure in the current production type of environment, or in a manual, when the driver is involved in the system. But think about this condition when the driver is not in the loop and something fails. We cannot afford to failed here because that is bound to create an accident. So the systems cannot afford to have a failure in such case. Now, how do we manage that? So this is those who are familiar with the power electronics side of the business. Now, the brushless motor, three-phase motor, is controlled by an inverter, and that's how most of the electric power steering systems work. And there will be a controller, logic, and DSP, and drive circuit, and power supply, and everything there. But the horse of the control is this inverter. So if something goes wrong here, now we just shut off the system and the driver just turns by itself. That's today's architecture. But that is not acceptable for the next generation of vehicles as we become more and more autonomous. So how do we do that? So this is an architecture which is in production again for one of the OEMs. They do use some level of autonomous control, so they cannot afford the system to fail. So we have a system in which we have two inverters driving the motor. So one inverter is the primary inverter, and if something goes wrong, we automatically switch to the other inverter and then warn the driver that driver has to take charge in that condition. But at least the driver has enough time to take control, and then we will get out of the autonomous mode also. So that is what this system does. Again, in this case, we assume that the not fail, the controller is the only one fails. Some OEMs. So this is the example of one of the systems which is in production. This is the two inverters. You can see these are all the power MOSFETs. There are a lot of power MOSFETs, and this is the DSP controlling the thing. And there are some drive circuits, etc. on this. So you can see the size of this. This is about 150 ampere controller to drive the electric power steering. The package looks something like this. The motor and controller are packaged. Now, so this in this architecture, really, we assume that the motor cannot fail. But that assumption, some people are not very comfortable with that assumption. For in such cases, we have another architecture where we have split the motor windings into two, and they are controlled by two different inverters. So if something happens, we shut off one, the other one will still drive. So at least we have enough power to get the vehicle to a safe stop again. So this is another architecture which is also being used. Now, I talked about the motor failure. Now, this is a picture of a stator of the motor. You can see all these wires crossing all over. Of course, they are all insulated, but now there is possibility that you can create shorts in that winding, so that can create fault in the motor. So avoid such situations is what is called a segmented type of stator winding, and these segments are wound and attached to to form the stator. So there is no possibility of short between the windings. So the severity of fault is now minimized, and so this is one way to make sure that the motor faults are minimized and eliminated. And so this is again another. So when you talk about the electrification in the transportation area, it's not only in the car. There are a lot of activities in the drones and the electric airplanes, and this is from IEEE Spectrum in 2019. Electric air taxi flies over Singapore. This is they are becoming more and more electric, even in the plane too. This is another one from June 2020, the IEEE Spectrum. This electric drones are carrying stuff from the ship and back and forth, and inflatable e-bikes, again, another example of electrification in the transportation. Now, with all this electrification, there are a lot of challenges also. Now, let me take one simple example of our car. Now, if you take our gasoline car, let's say we have a tank of 50-liter tank. The energy density of gasoline is about megajoules per liter. If you calculate the total energy of that 50-liter tank is about 1,600 megajoules. Now, if you think about pumping the gas or pumping the petrol or gasoline in the car, it takes about a few minutes to pump the gas. Let's assume that you took 3 minutes to pump that gas. And if you calculate the power transferred during that time, which is nothing but energy divided by time, you can see that you are about 9 megawatt of power. So when you are going to the gas station or pump station and pump the gas, you're transferring about 9 megawatt of power for that 3 minutes of time. You may not be thinking about that. If you're talking about electrical stuff, 9 megawatt is a huge power. So if you take a Tesla Model 3 battery, its pump capacity is about 85 kilowatt hour, which is about 306 megajoules. You can see that it is actually much lower than the tank capacity. But the reality is this energy is, a lot of that energy is being wasted because the IC engine has the efficiency, very poor efficiency. So these two are probably very similar in terms of the range of mileage range or kilometer you can drive with this car. So in Model 3 with the 85 kilowatt hour can probably get the same range as the 50-liter tank. Now, when you talk about the charging options, okay, if you can charge that battery, I'm again taking the same Tesla 85 kilowatt hour battery. If I take the charger capacity on the x-axis, and if you have a smaller charger capacity, the current is small. As the charger capacity goes up, the charging current goes high, but the charging time is inversely proportional. When the power is low, it takes a long time to charge. So if you take most of the electric vehicles, they all come with what is called a level 1 onboard charger, which is less than about 1.5 kilowatt type of power range. They take anywhere from a couple of days to charge the car, really. Okay, so that is the normal built-in charger. Now the other Level 2 charger is defined somewhere in the 3 to 20 kilowatt type of charger. This is an external charger to charge the battery in the car. They are designed such that you can charge the car probably overnight. So if you plug it in once you come back from work, next day morning it'll be fully charged. So that's what that level 2 charger is. Now, if you think about refueling a car, which is done in 3 minutes, if you want to achieve that, the level 3 is really about 100 to 150 kilowatt. Even with the level 3, it takes at least about half an hour to charge the car by about at least to the 80% level. So even with the level 3 charger, we are way behind in terms of the refueling time compared to the present IC engine cars. So this will be a challenge in terms of how do we charge it faster? How do we how can I get the battery size low? These are all the challenges. How do we manage the charging centers? If you talk about 150 kilowatt charger for a half an hour charger, if you have 10 systems in a charging station, you're talking about 1.5 megawatt systems there. And the charging, how can I minimize the charging time? The power system impact on these chargers, with the chargers, are all a lot of work going on in all these areas. And the power system load fluctuations due to EV charging. And another aspect is really, is the electric vehicle really making an impact on the net emission? Because one of the biggest thing which we talk about with electric vehicle is that it reduces the emission. But if you think about it, if you are charging from your grid, which is made of the grid power is coming from coal and polluting fuel sources, then really what electric vehicle is doing is moving the the emission from one area to another area. But if the power grid is really renewable energy based, then really we'll have an advantage. So these are also challenges in terms of how do we manage all that stuff. Now this picture is from actually this month's IEEE Spectrum. If you have received it, you'll see that now this is how do we charge the system on side. Now this is a wireless charger, especially for the buses, which normally goes and stops at all the bus stops for maybe a minute or so. At that time, you can use the charger to charge the charge the bus, so that every bus stop when it is stopped, it is being charged. So you can improve the miles you can drive with this type of technology. Now, again, this is new in terms of there are a lot of people working on this type of aspect. These are only development examples here. Now, another huge challenge is really the battery. As I said, the battery. If you look at the electric vehicle, the biggest weight and biggest cost in that vehicle is the battery. The battery cost is coming down. We are somewhere around, I think, $200 per kilowatt hour, and by 2030, it's expected to come to about $60 per kilowatt hour. These are all predictions. Okay, this can change, but I'm not an expert in the battery, but there are a lot of research going on in the battery area in terms of improving the energy density, thereby reducing the size and weight and reducing the cost too. So these are areas where a lot of work going on. Again, I don't want to claim any expertise in that area. Again, from last month's IEEE Spectrum, ultralight batteries for electric airplanes. They talk about a few of the developments and some of the new things which are going on in the battery. If you're interested, you can look at that. So some of the important considerations and challenges in the design is really, especially in the automotive sector, cost effectiveness is very important, because you can have all smart things and everything. If it is too expensive, nobody will buy it. So we have to make it cost effective, smaller packaging and higher efficiency. As I told you in the beginning, the cars are not made for transporting motors and controllers. That cars are made for transporting people and his contents from point A to point B. So they don't give you much space for packing all the electronics and motor. So we have to make it very, very small so that you can package in a very small space. And higher efficiency. When you talk about efficiency, you may think that the higher efficiency major impact is on the miles you can drive. That is one of the aspects. But the other major aspect is really, if you can make the system more efficient, the thermal management will become much easier. Thermal management is a huge challenge in all these systems, where you have to take the heat out somehow from all these electronics and motor and everything. So if you can make it more efficient, so the taking heat out becomes much easier. Fault tolerance, as I said, with safety critical systems, the fault tolerance becomes very important. Diagnostics capabilities and self-diagnostics and smart devices. Can you have devices which can tell you that before it fails, so that we can give you warning beforehand, so that we don't have to wait till it fails. So these are areas of work that needs to happen. And of course, the fail-safe operation and redundancy requirements. And another important thing in the automotive sector is the audible noise characteristics. When you are, again, from a steering point of view, when you are steering your car, you don't want to hear the motor noise or controller noise or something coming from there. So we have to make the system very noise-free, and that is being done by motor design, controller design, and the control aspects. And these are the things which controls that. And of course, the higher temperature operation, under hood temperatures can go up to about 150, 120, 130 degrees. So that environment, this controller and electronics has to survive. Now, why is this electrification happening now? If it is all this great and good and advantages, why didn't we start thinking about it 20 years back or 30 years back? I think there are several reasons. There are significant improvement in the power electronics capabilities. I showed you the MOSFETs which are sprinkled on the board. The MOSFET performance has improved tremendously. Today, these power MOSFETs are nothing but the switches. When that switch is on, it is pretty much like a conductor. So the losses are very, very small. And the cost of these devices are also has come down significantly, so that again, in that system, we were using about 22 power MOSFETs in one unit, and the costs are come down so much so that we can afford to do that today. And new wide bandgap devices like gallium nitride and silicon carbide is going to make a huge difference, especially in the traction type of in the high voltage systems where MOSFETs are not very highly efficient for that type of application. So the performance and cost of the are coming better and better with the the wide bandgap devices like gallium nitride and silicon carbide, which is going to help quite significantly on the traction drives. Significant progress in the processing and control capabilities. Now, I told you about the safety things we can do in the car, but that is all possible only because of the processing capabilities which we have today. When I started working with the steering systems, we were using an 8-bit processor, microprocessor, which was really not at all powerful. But today, you tell what algorithm you want to put to control the motor, the field-oriented control, flex vector control. In addition to the steering system control and all the safety aspects, we can manage all that stuff with one digital signal processor. And the cost of that is also coming down. And invention of the high energy magnets and improved manufacturing process for motors are reducing the cost and size of the brushless machines. And that is also allowing us to make the systems smaller and more efficient. Another very important factor is really the efficient analytical tools for design optimization. Today, I can predict and design the motor very well without making the hardware. I can predict the performance very well because we have 3D finite element models and 2D finite element models and all. We have very good confidence that these things are giving me the right answer. And not only for the motor design, even for the controller and the thermal aspects, all these things without even making a unit, we can predict the performance very well with the advanced tools, and they are very fast. Some time back, 3D finite element used to take a long time, and today it is not that bad. I mean, still it is too much, but I think it is improving day by day. So we'll see more and more improvements in that direction also. So with all that stuff, what is our role? We as engineers, we have to design our systems to achieve our final goal. As I said before, we may be proud that we are a power electronics or a software or a machines or a sensor or control algorithm expert, but that has no meaning if we cannot integrate that into the final system to create the final unit. So it is our responsibility to design the systems and integrate the system to achieve the final goal of this. So we all have to start thinking as systems engineer, so that even though you are a control systems engineer or a power electronics engineer, you are designing your component to meet the system requirement. If you don't understand that, if you design your part vacuum, that will not be a successful design. So we all have to start thinking more as a systems responsible person, even when we are an expert in a certain area. So we have to integrate all these mechanical systems with the mechanical systems to create safe mechatronic systems. And I think that is our responsibility and challenge. So to conclude, I think, if you look at the last 20 years, we have witnessed tremendous progress in innovations and technology applications to the real life. Now, if you look at the communication systems, medical system, transportation system, social media, and all the communication associated with that, we have made tremendous progress. And maybe if I say, 20 or 30 years back, if you were sitting there and thinking, what will happen in 30 years, we might not have even thought about some of these things. That's that much of progress we have made. So what will happen in the next 20 years? One thing I can say is, it's a good to be an engineer, because it is interesting, and it is challenging to be a part of this next generation technological revolution. Now, how does the next 20 years look like? I think it is up to all of us to define how that will look like. And I think you all will be a part of that revolution. And hopefully we will, 20 years from now, we will look back and say, oh man, how much progress we made. And it was nice to be a part of that revolution. I think with that, I will stop it here. I would rather spend some time discussion, and if you have some questions, I would like to discuss that.
Any question, please write to Tomy sir directly in chat box.
Oh, so you want to go through the chat box? Is that what?
Yes, in right hand corner, box is there.
All right, let me see if I can read it. How to integrate the complex electromechanical. Give me 1 second. How to integrate complex electromechanical electronic system in the design stage? Good question. This is where I was saying that we cannot design our system in vacuum. I showed you the picture of the motor control unit which we are using for the power electronics. So if you think about that, that motor, the motor housing, the mechanical design, the electronics, everything is integrated. The heat sinking is done through the motor housing, from the power electronics to the motor housing. So the thermal analysis is all integrated between the electronics and controller. So this is a good example to say that this is really a complex system where the machine engineer, the power electronics engineer, the mechanical engineer, all these people are working together to integrate these things. I cannot sit and design and say, no, this is the motor, you take it. That doesn't work if you want to do this electromechanical and electronic system design integration at the design stage. At the design stage itself, we have to cooperate and make trade-off between each one. You may be able to save a lot of money in the controller if you spend little extra in the motor, or vice versa. But then we have to optimize and say, which is the optimum condition so that we can minimize the total cost of the system. So this is not an easy answer, but I think the real challenge is going to be working together as a team with the various expertise so that we can pull all these things together. Okay, I hope I answered that one. Let me see what is the next one. What are the decision algorithms used in electric vehicles? I'm not sure what exactly is meant, but let me talk based on what I understand. if you look at any algorithms, they are all decision based. Now, if you look at let me talk about the steering systems, which where I'm working more closely. We have automated driving systems where we have position control in the steering, and driver doesn't have to touch. They are all decision-based algorithms. You have inputs coming from various sensors, and each of that sensor is giving you some information, and you have algorithms in there to make the next step, make the corrective actions, or make whatever is needed. Even not only that type of control, even for protection systems. Let's say that the system is overheating because of some failure or something. You have to monitor that and make the decisions. Again, these are all algorithms which are making these decisions based on the sensor inputs. That becomes very common in all these systems. I lost my chat box. Something happened. I need to get back to the chat. Okay. What about the scope of wireless charging systems in India? I don't know whether it matters whether it is in India or any country. I think to me, the technology has not developed to be commercial yet. Okay, so people are concerned about the EMI issues and the how does that field affects the humans, and these are probably all not scientifically proven things, but we still have a lot of work to do in all that, and how efficiently we can charge. I'm not an expert who is working in that particular area. There are a lot of people who are working in that area. So ultimately, that's the best way to charge it, if we can make it efficient and without any issues. So just like what we saw in the case of the bus which I showed, even for auto stands and things like that, we can think of wireless charging, so that when the auto is waiting for something, you can charge it. So these are all possible, but then we have to create the infrastructure to do that. So that becomes another challenge for that. Okay. So these are all challenges which we have to face and address. How can we guarantee about the design software genuinity? Okay, good question again. I think in the software level today, we have what is called standards. I talked about the ASIL level standards, and for the software, there is what is called SPICE standards. So we have what is called SPICE certification. In order to get SPICE certification for any company who is writing software, you have to follow certain guidelines. Now, these guidelines are all there to minimize the errors that can happen in the software. Again, to me, you can do all these things, but still ultimately you will create some errors. So we go through a lot of testing to make sure, especially in the automotive sector, we do a lot of testing to make sure that we have no errors and bugs there. Now, in that respect, I have to also say that, the next generation of vehicles, you will see that all these vehicles will be equipped with over-the-air software loading capability. So if with that, what happens is, once the vehicle goes into the market, if the OEM finds that we can improve some of the aspects, they can download the software again. So today, if you remember in US when Tesla came up with their car, they have the capability to download the software anytime they want. So at one point they said, okay, tomorrow onwards your car is capable of driving autonomous driving. They downloaded the software to do that. Of course, the hardware has to be capable of accepting that. Once the hardware is set, the software can be downloaded later on. So that is a huge advantage to address some of the issues that could emerge basically because of the software bugs or anything. But we do a lot of we put a lot of emphasis in terms of testing and even worst case conditions and outside the operating range to make sure that even if something fails, that's a safe failure. So that there's a lot of work going on in that area also in terms of the software, how cleanly we can make the software. When do you think graphene battery is commercially viable? Again, as I said, I do not want to claim any expertise in the battery area. The only thing I know is a little bit of reading, which I do. And that's why I was referring some of the IEEE spectrum articles which came out recently, which shows there are a lot of different technologies being worked on, and I really do not know which is going to be the winner at the end of the day. Whichever battery which is the highest power density or highest energy density and lowest cost is going to win, and who is going to come up with that and what technology is that going to be, I have no idea. They talk about solid state batteries. If you think about the storage medium, 10 or 15 years back, if you're talking about a 1 megabyte storage, we were talking about the tapes and disks and all that stuff. Today, several gigabytes can be put in a small solid state memory. So, that development happened in the last few years, and you can probably think of similar type of developments in the battery area also. And so I don't know which one is going to win, and so I will leave it up to you guys for that. Okay. What are the upcoming trends in motor designs? Let me say something which is a continuation of my preaching before. We need to design the systems for an application in mind. Now, we say that we optimize the motor. This is the best optimal. You'll see the papers in the articles optimum motor, optimal design. What is optimal means? Optimal in my mind means that for the application, it is optimal. So if I have a motor which I designed for an application, that may be the optimum for that application, that may not be the optimum for some other application. So keep that in mind. So when I was showing some of the designs, which design trends in the automotive sector in terms of the segmented windings and the elimination of the distributed winding to minimize the probability of short between the windings and phases and things like that. These are all critical for the safety critical applications. So that is what the trend in the automotive industry is. Now, do you need that in every other industry? No. Okay, so it is up to the we as the design engineers have to look at the application and decide how we want to design that one. Now, in terms of trends, design trends, I would say the finite elements capability is tremendous now. That anybody who is in the design of the machine should make use of that one, so that we can design the machine optimally and take out the unnecessary iron and weight and things like that. So that is one of the designs. So the analytical tools is probably the biggest trend in my mind. Also considering human factors. I'm not sure what that meant. How fast should the battery be charged itself if it have to be done at the stop? Is it very fast? Okay. The idea of the bus stop charging is not to charge the battery fully at that stop, because the bus stops often and stops at every bus stop maybe a minute or two. If we can charge in that 1 or 2 minutes, let's say just for the sake of argument, let's say you have a 100 kilowatt charging system, and if you can, let's say 60 kilowatt for easy calculation. If you have a 60 kilowatt and if you are charging for 1 minute, we already got 1 kilowatt hour charge into that battery. So each stop, it is able to recharge, replenish some of that charge. You may not be able to fully charge it. That's okay, because at the end of the day, the bus is going to be placed at some place where they can charge it fully for the next day drive. So the objective is really not to charge it fully. How is it? So it's not fast enough to charge it fully. It is only to refurnish the charge. Okay, what part of a computer science engineer can play in developing these systems? I think the previous question of the software, there is a lot of work which are really happening in the computer architecture and everything to make this fail-safe systems. Cyber security is one of the aspects. These are, I mean, if you look at the digital signal processors that are coming out, they must have the cyber security capabilities. Who is implementing all these things? They are all computer scientists and the architecture engineers are the one who are implementing these type of things. How do you minimize the software bugs? What type of architecture we are using? And we also use quite a bit of auto coding type of things. They are all coming out of the computer science area. That they all minimize the amount of errors that when human beings are writing the code. So we can minimize that by these are all engineers, whether you want to call it as computer science engineer or computer engineer. These are all people who are in that area who are producing that. I am working on AI with listening network for research. How? Oh, okay, that was only a comment. There is one more. How much time I have? I think your session starts at 12:30. I mean, what is time now there now? It's 12:30 in the night here. 10 o'clock there now?
Yes, 10 o'clock.
So your session is starting at 10 o'clock. I should probably stop it here, I think. Is that right?
Yes, sir.
Okay, I'll take this last question. Titanium dioxide is an alternative MOSFET material. I do not know about that one. The only material, only thing which is at least commercially viable are the MOSFETs and the wide band gap devices like silicon carbide and gallium nitride. So, okay, so I'm sorry. I think I will stop it here so that you can start your session on time. I don't want to delay your session. I think there are more questions on these things. If you want to take a few more questions, I can. Otherwise, I'll stop it here.
Sir, I will share your email ID to all participants. They will ask your question on the email. Only.
Okay. All right. Great. Thank you so much for all the wonderful questions, and hope I was able to convey what I wanted to convey. Okay. And
so many questions, because many are willing to ask question, but time is limited. That's why we should stop here.
Okay. Thank you. Thank you. Thank you all. Have a wonderful conference. I will see you this evening there. Okay.
Sarwan sir, please give the formal vote of thanks.
Yes, thank you, sir. It's my great pleasure to pay the gratitude for your enthusiastic, informative, and technological knowledge sharing with us. We had started with our day a wonderful information on the developments in vehicle electrification. The students and researchers can work on various challenges in integrating the mechanical and electrical parts to make the system more responsive, which is hardly need for an alternative. Thank you so much, sir, for your valuable time and support towards our conference. Thank you all.
Thank you all. Have a good conference.
Thank you, sir. Sir, YouTube link and all the YouTube link already shared to you, sir. YouTube link this picture.
Oh, I'm sorry. What is that?
YouTube link. YouTube. Actually, this will run. Actually, sir, also run in YouTube also.
Oh, okay. Okay. All right. Thank you.
Thank you, sir. Thank you.
Thank you, sir.